Hello, Professor. Here is Kai-Xing Hao and Jia Shen, and we are here to give a brief presentation on our final capstone project on adopting adversarial training to optimize multi-stakeholders in recommender systems. For the agenda, we divided our presentation into three parts. The first one is motivation, literature review, and inspiration. The second one, data metrics in our model. And finally, the empirical results and conclusion. To begin with, recommendations are used in various online platforms, and we find that the biggest limitation of widely used recommending algorithm is the overemphasis on users. Specifically, many algorithms aim to optimize matrices that measure the accuracy, diversity, and novelty of recommendations to only users, leaving behind the interests of other stakeholders. Solely focusing on users can be detrimental. It will amplify the imbalanced distribution of items, causing the long tail effect and leading to under-recommendation item bias. Such a situation can stimulate conflicts between multi-stakeholders, and it is unhealthy for the platform and even society. As we explore more relevant literature, we find it both interesting and valuable to solve the contradiction between the multiple stakeholders in the recommender system. We want to find a more dimensional way to measure the interests of different stakeholders and build a framework or an algorithm to maximize the benefits of the whole system. We started by finding traditional ERM model. He developed neural network-based collaborative filtering, aka the NCF, as a simple framework with MLP instantiation, which serves as a guideline for us to develop deep learning methods for recommender systems. Unlike the ERM-based model, Edward proposed a constraint-based inter-programming optimization model in which different sets of the constraints are used to reflect the goals of the different stakeholders and model the recommendation output as the decision variable. However, Srivastawa proposed an adversarial trained model with fairness considerations and extends them to the recommender systems. He showed that directly applying an adversarial model to the training of the recommender system without the modification of loss function can fail to generalize well, but a carefully structured adversarial model can perform much better. We noticed that the model proposed in this paper is not under the context of multiple stakeholders, which is what we are going to explore further in our topic. The other thing I want to mention here is the reweighted learning. This can be used in situations where the training data is unbalanced, and reweighting the data can help to improve the performance of the model. In the context of the recommender systems, we can give more weight to specific user groups, item groups, or certain interactions. Previous works have demonstrated the usefulness of item-level reweighting. However, in our work, we decided to experiment with the interaction-level reweighting between both the user group and the item group.
Okay, here is our solution. This is the overview of our progress. We first choose the NCF model, which is Neuron Collaborative Filtering, as our baseline model. And then, inspired by the Lahoti 2020, we adopt the adversarial weighted learning techniques, hoping to improve the overall performance on the recommendation task, since we believe it can take into consideration the tug-of-war between multiple stakeholders and deliver more reasonable recommendation results. And finally, we use 5 metrics to evaluate the model performance, which will be detailed on later. And next, we will briefly introduce the dataset that we use. The dataset we use is the movie lens dataset, which is widely used in development and evaluation of recommendation algorithms. The dataset includes the ratings for a variety of movies, as well as the demographic information about the users who provided the ratings. We used the movie lens dataset to reproduce the PyTorch version of the neuron models in our project. For example, we trained the NCF and ARL model to learn the embedding of each user and item, which then generated a score for each user-item interaction pair, and then returned a top K recommendation list for a specific user among all the items. And we then process the dataset using the techniques called the negative sampling. As shown in the picture, for each interacted item of a specific user, 100 uninteracted items, which we call negative items, are then sampled from the dataset. And the purpose of this is to apply the hit rate and NDCG metrics, which will be introduced later, to evaluate our recommender models. Now we will introduce the evaluation matrix that we pick. And the hit ratio matches whether the recommender system is effectively recommending items that the users find interesting or useful. And the higher, the better. And normalized discounted cumulative gain measures the relevance of an items that are recommended to a user. More specifically, it equals to what degree the order of the recommendation list is optimized, and we also expect it to be higher. The Gini index and entropy are quite intuitive, which intake a recommendation list of movies and output the diversity of our recommendation results. And we are expected to have a higher value of Gini and entropy index, meaning that the recommender system put forward various genre movies rather than just focusing on some homogeneous topic. And then finally, the index for the items, which is called long tail proportion. So we first define the long tail item to be those items that appears less frequently in the recommended lists than in the whole data set. And it's reasonable to treat items as a stakeholder because it reflects part of the interest of the content provider. Now it comes to our model architecture. Figure 1 shows the architecture of the basic NCF model. And the model takes in a concatenated embedding of user and item as the input of a multi-layered neural network. And in this network, the ReLU function is chosen as an activation function between each layers of the neurons, as shown on the right. And we then output the logics, use Adam optimizers to train a model with interchangeable loss function. And the ARL model is implemented based on the NCF model. And this model contains a learner model and an adversarial model. The adversarial one outputs a weight vector that multiplies with the logics output from the learner model and computes the adversarial loss for model training. And the adversarial model is proposed to balance the probability that an item will be recommended across all users. And for the hyperparameter, there are many things that we can choose for the model. And we are particularly interested in tuning the number of negative items from 100 to 1,392 to achieve a modified full-scale evaluation. This can be quite challenging considering there are over 1,000 negative samples and only one positive sample from which the model can choose. And then we tested two different top K recommendations with K is equal to 20 and 100 separately. And also the choice of loss function is also a hyperparameter where we try to test whether different choices of loss functions can improve the model's interpretability. For example, we interchangeably choose between the binary cross entropy loss and the hinge loss as our loss function.
This table summarizes the empirical results of our experiments. As we see in the first two columns, we tried different combinations of the hyperparameters, that is, top K and negative samples. We tried three different combinations of the hyperparameters and applied them to the base NCF model and ARL model. As we see in the table, adversarial training actually decreases HR and NDCG for both experiments. And we may also notice that Gini index and entropy coefficient are almost consistent throughout all the experiments. And finally, we have the user-centric evaluation function, which is the frequency of long-tail items in the recommendation list. This number also stays the same in every experiment. From the results, we may further conclude that although adversarial training proved to be efficient to benefit worst-case users or worst-case items, it has negative impacts on average user utility and have zero or non-significant impact on average item utility, which means that we think adversarial training can be useful to improve the worst individual level utility, but this approach struggles to handle or to improve the general level utility. Our work concludes that adversarial training cannot help us to consider more stakeholders beyond users, and therefore cannot be used to improve their utilities too. But as our work does not aim to beat the NCF baseline, we wish to provide only empirical guidance on future work that adversarial training may not be ideal for solving the multi-stakeholder problem in recommender systems. At the same time, this could be because of the limitation of our work. For example, previous authors have indicated that the design of adversarial networks plays a significant role in determining the results of evaluation metrics, because our work only examines a few variations of the adversarial architecture. That is, we have first the embedding layers, and then a simple, fully connected neural network with a sigmoid activation function. We believe future work can try different combinations, like different user and item embeddings. They can replace the linear layer with more complicated architectures, or they may use different activation functions in each neuron. And second, in terms of adversarial training, this work will weighs the data points from the interaction level. But we believe future work can apply the adversarial training to reweight the users or user groups or item groups. That is different from our interaction level focus. And finally, we believe future work could also try adversarial loss that is different from hinge loss and binary cross entropy loss. For instance, they may change the adversarial loss to NDCG loss, and we believe it is likely to make the model perform much better in the NDCG evaluation function. This is our work. Thank you.